of you. One more. Okay, people. I think we'll start. Right. So, guys, ready? Are you able to hear? Everything is okay?
Yes.
Yeah. Okay. So we'll continue doing with the problems, and then we'll continue with the concepts. Okay. So I have this question. So they have given you a diagram. Okay. So people, I wanted to find what is this T, and also I wanted to find what is the work done in this. Okay. Can you do it? Now again, so many information is given to you from the diagram. Okay. So first thing you'll be able to easily understand what kind of process it is. What kind of process?
Sir, adiabatic.
Yes, it's going to be an adiabatic process because Q is equal to 0 is given, right? So the system goes from this state to this state without any absorbance or without any loss of heat, right? So obviously it's going to be an adiabatic process, and they didn't give you anything specifically about whether it's going to be reversible or irreversible. So obviously we'll be considering only reversible, right? Okay, so we know what equation which you have to use. What equation I have to use for finding T? How will you find out this T? There is one equation which is going to help us, right?
PV gamma minus 1.
Yes. So we have derived this Tv power gamma minus 1, or say T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. So all the other things are known. Just T2 is what is required, isn't it? Right. Okay. So now we know what is gamma, or say what is gamma minus 1, right? Gamma minus 1 is basically going to be
R by CV plus 1.
So gamma is R by CV plus 1, right? So gamma, or I can write gamma minus 1, is basically going to be equal to R by CV. Okay. Now I want someone to answer. Let me see who is there. Okay. Let me ask. I don't know who the keyboard lovers is. Whomever it is, are you there? Does anyone know who's the keyboard lovers?
It's Mithun, sir.
Mithun.
Mithun. Okay, Mithun. It's Mithun, it seems. Okay, Mithun, are you there?
So whenever I come in Zoom, it automatically changes its name. I'll click the rename option and I will change the name, sir. Every time.
No problem. Anyway, so I want you to tell me what is the CV value for this particular problem? What is the CV value? Sorry, CV value for this problem? Mithun, are you there?
R, sir.
Odd? What do you mean by odd?
R, sir.
R. Okay, just R. No. Okay. Okay. I'll ask maybe. Okay. Surya, are you there, Kana? Surya Muthu. Surya.
Sir, for 5 minutes I won't be there, sir. There's some work in the home.
Okay, cool. No
Yeah,
issue.
I'll be back in 5 minutes.
Sure. Take your time. Okay. Then maybe Venisha. I know you're not able to maybe use your microphone, but you can put it in the chat box. Venisha, what do you think will be the CV value for this question? Just give me a yes, and then you can start typing because I just want to know whether you're there. Okay. Yes. Tell me, what will be the CV value for this question? No. I'm not asking volume. I'm asking the CV value. What will be the CV value for this question? CV value is heat capacity at constant volume. Okay. So I'll assume that you don't know. Can I?
Sir, is it 1?
What do you mean by 1?
Sir, you said that in the start that there will be no heat this reaction.
Okay.
So
it will be 0, sir.
Guys,
Sir, 3 hours,
okay.
sir.
Yes. Okay. Yes. 3R is the correct answer. Now, please, and see, it doesn't depend on the process. It doesn't matter whether it's adiabatic or isothermal or isochoric. It really doesn't matter whether it comes to CV. CV is a constant value, right? The only thing which
Okay,
is
sir.
going to depend on, what is it going to depend on, people? The only thing which is going to depend on,
Type of atom.
exactly, what type of gas I have, right? Whether it's monatomic or diatomic or polyatomic gas. That's the only thing CV will depend on, right? So they have given you ammonia. So definitely ammonia is a polyatomic gas. Okay. So for polyatomic gas, I know all 3 types of motions are possible. That is translational, rotational, and vibrational motions are possible. So you have to sum up all the 3 contributions by the motions. to the CV value. And we know that for translational motion, it is 1.5 R, and for rotational motion, it is 0.5 R, and for what is that? Vibrational motion, it is R, just 1 R, right? So now this molecule has all the three, what is that, motion, types of motion. So definitely you will see that I'll sum it up. I'll be getting 3 R as the CV value. Guys, you have to know this, right? See, we have done at least, I don't know how many problems, at least 3-4 problems on finding the CV value based on what type of gas we have, right? So be very careful, right? Okay, so just you have to substitute this value here, right? So gamma -1, so R divided by CV. CV just now we found out to be 3R, so it's basically again going to be 1/3. I can just keep it as 1/3 because it's cube root. We're going to go to the powers, so it is going to be helpful, right? So I think that's it. Now you can tell me what is this T Kelvin? What is this T? Go for it. Find it out. It involves some calculation. I'll give you 2-3 minutes. Quickly go for it. Is one didn't answer. Everybody understood. How is it 3R?
Yes, sir.
Yes, sir.
Yeah. Hope you're all doing it. I'll also do this side. So, okay. So I'll write it here. So T1 is 300 into volume is 100 power 1/3 because it's gamma -1. I just found gamma -1 RBC substituting into T into 800 power 1/3. So I think we'll be able to get it done. This
Sir, doubt we have to convert it to meter cube, no, sir?
not required because anyways it will get cancelled on both sides. Yes, right?
Yes.
Anyways, they will get cancelled. Both temperature Kelvin as well as whatever the unit you're going to use for volume will get cancelled. It doesn't matter, right? Okay, so I'll be getting T as basically, so this will go down here. So 300 into 100 divided, sorry, 100? Yeah, 100 divided by 800, the whole power 1/3. So done. So it's basically going to be 1/8. So I know a cube root of 8 is what?
2.
Right. So cube root of 8 is 2. So I basically have 300 into 1/2, which is going to be 150 Kelvin. That's the answer. Right. So T we have found out. Next, what you have to any questions, people? Nothing. I just substituted. If I do my calculations properly, that's it. I get my answer. Temperature value as 150 Kelvin. Done. Easy. Right. So next, what I have, they have asked you one more question in this thing. So you have to find the work done also, right? And guys, please understand, you are not going to find the work done here through P external del V. No, we will not be using that equation, right? So whenever you have an adiabatic process, right, and they ask you to find the work done, you always know that in an adiabatic process, delta E is equal to W. Is it not? You can again derive it from the first law. Delta E is equal to Q plus W. In an adiabatic process, Q is equal to 0. So I have delta E is equal to W. As simple as that. Right? Now all I have to find is my W. So if I can find delta E, and that is obviously equal to my W. You should not use minus P external del V. Even if you want to use, you don't know what is the external pressure. So don't go for it. Right? So you know all the other things, but you have no clue about the external pressure. Like only if you know, maybe then you can apply. But even if you know that, I would suggest you to go by this method only. Find delta E, and that eventually is equal to my W. Right? Okay. Now, what is the formula for? Okay, wait. Now I'm gonna ask someone. Who should I ask? Maybe. Okay. Abhishek. Are you there, Kana?
Yes, sir.
Abhishek. Kana, can you tell me what is the formula for delta E?
1 second, sir.
Yeah. I think there's a glare on the board right here.
Yes, sir. Yes, sir.
Okay. 1 second. I'll correct it by the time you give me the answer.
Okay, sir.
I have a doubt here.
Yeah.
Sir, why can't we use W equal to 2.303 NRT log V1 by V2?
Okay. Fine. I'll ask you a counter question. For what process did we derive that equation?
Isotherm, sir.
Okay. That's why we done it. It's an adiabatic process. Right? So yeah, are you up with an answer, Abhishek?
Sir, is it EF minus EI?
Obviously, it is going to be F minus EI, but we have derived an equation, no? In terms of CV and stuff. Okay, no issues. At least now you'll know. Okay, Shruti, are you there?
Yes, sir.
Can you tell me what is the formula for delta E?
Sir, del H plus W, sir. I think it is for isobaric process.
No, it's correct, but how will I use that here? How will I find it out? Like in terms of CV, we had an equation, right?
But it involves logarithm, no, sir. Like CV log T2 by T1, that.
Like anyway, so okay. Now please understand. Even though okay, now we know that we look okay. It's a good question basically. So we know that we have how to put it? A delta E is basically a state function. Like even though you go for small changes, integrate and all that, eventually it is going to be only a state function. It depends on what is the initial state and what the final state. But W is not like that. W is the path function. Maybe I already discussed state and path functions, right? So W is the path function. So there the integration matters. Okay. So in this case, I can directly put the whatever the formula which I know. It is gonna just depend on what is the initial temperature to be specific and the final temperature. That's it. That is how it is going to depend on. So if that's the case, what will be the formula here?
And T2 by T1 equal to V1 by V2 the whole R by CV.
No, okay.
NCV delta is.
That's it, right? It's just that formula, NCV del T. That's the formula which we have derived. So I know N number of moles is given. CV, we know delta T. Again, we have found out. How we found out? Because I know T2, I know T1 both. Guys, whenever I ask you what is the formula for delta E, this is the first thing which should come to your mind. NCV del T. This is the first thing. Not for everyone, this is the first thing. If you're not able to use this, 99% of times you'll be able to use this formula blindly, right? But if at all you're not able to use it, and all the other formulas you told me, delta E is equal to delta H plus W, all these things.
So doubt, sir.
Yeah.
This isn't for the particular process, no, sir. This formula.
No. For any process, you will be able to use this equation.
Yeah, okay.
Okay. Any blindly you can use this, irrespective of what the process is. Right. I'll be able to. This is because that is how I define my delta E. So you don't have to worry about it. Irrespective of what the process is, you can use this, right? Very rarely, very rarely you will be going for other formulas, say the delta H plus W and all that. So from the question itself, you'll be able to understand whether I'll be able to use that formula or not, right? We will do problems just like that. Whatever formulas you told me, we will be doing problems, but you will be able to understand. Okay, at that time I have to use this, but majority of the times you will be using this formula only. Okay, so next time if I'm asking and nobody's going to answer this question, delta E is equal to NCV del T, that means that I don't know, or like either how I don't know how else to tell it more clearly, right? So this is the formula which you have to remember for delta E, right? So I can just substitute it and get the answer. So number of moles is 1, CV we just found out it is 3R, and change in temperature I just found out my final temperature is, it is going to be T2 minus T1, right? So T2 I found out to be 150, and initial temperature was 300. So definitely here it is negative, right? So basically here it is going to be 150 minus 300. So it is going to be minus 150 Kelvin. So yeah. So it will be 3 into minus 150, which will be minus 450 R. And you can put the R value 8.314, obviously. Yeah, because you're finding the answer in terms of joules, right? But in the particular question, they're asking in terms of calories. But we are not doing calorie problems because no, they're not going to ask you on board like in your school exams. Like they'll ask you only in joules. Okay. If I ask you in calories, we know what value of R we should use. R value should be 2, right? So in this case, R value is 8.314. Just substitute it and get the answer. That's it. Okay. So I hope everybody understood.
Yes, sir.
Right. Okay. One more question. Okay, a question. 2 moles of an ideal diatomic gas. 2 moles of. Okay, if you're taking this down, I'll give you a minute. I can copy this. Then I can start. And yeah, and guys, I don't say good news. Good news for me, but I don't know how. It's just that I'm like in another next maybe from next week, right? So you will not be seeing this board and markers and these things while I'm teaching. So I'll be using my laptop, right? And basically it's a touchscreen laptop which I ordered, so it will be coming in another 2-3 days, right? So I'll be using a stylus. How your physics sir teaches, right? I think he uses a tab, he uses a pen to write,
Yes,
and
sir.
then he'll be sharing a screen, and then his face will be small, like in the corner it will be visible, right? So I think that's how he teaches, and we will be continuing like that. Okay, and if at all you find that sir, no, that was better and stuff, then we can come back to this, right? Because obviously this is the first time I'm going to use those kind of stuff, right? So it might be there and there. I might say, how to put it, I might not do good. Like maybe I'm not so used to all these things, right? So at that time, yeah, if you can tell me freely, like sir, no, that was better, the board was better, so this is better. If you have any things, you can always let me know, right? And accordingly, we'll take a decision. Is that okay? So like basically, this is I have become very comfortable with this because this is what we have been doing for so many years. I mean, I have been doing for so many years using boards and markers and teaching. But yeah, this is very good. But this is okay, what you understand is basically there's a phone, like there's a like here from where you're seeing this is a phone, right? And this phone is mounted on a phone stand. Phone stand in the sense you have seen people, right? They'll have a tripod stand, and then they'll be using for cameras and stuff. So basically, I have used a tripod stand, and the phone is standing on this, right? And again, you can see there's a board, and then for this there is a stand. Okay, this is the thing. Right, that is a stand. So it worked out, right? Because the camera is very close to me, that's so that there's no problem, right? But if I want to travel, right, if I want to go somewhere, it is really a problem. I cannot carry all these things and go. So that's the main reason that I'm buying all this, right? So we'll see how it goes. But I actually prefer, right, I'm little enthusiastic when it comes to explanations, right? So if at all you're not able to see me, maybe I'll not be okay with it, right? So we'll see what can be done. Okay, fine. Anyways, so yeah, continuing with the question. So 2 moles, yeah, what you're writing. So 2 moles of an ideal gas, ideal diatomic gas, 2 moles of an ideal diatomic gas undergoes reversible isothermal expansion, right? 2 moles of an ideal diatomic gas undergoes isothermal reversible expansion at 298 Kelvin. At 298 Kelvin. From
Sir, sorry, sir. Undergoes.
Yeah.
Undergoes what? Sir?
undergoes an isothermal reversible expansion. It undergoes an isothermal reversible or reversible isothermal expansion, whatever it is, right? At 298 Kelvin. At 298 Kelvin from 1 bar and 49.6 liters. Okay, this is the initial state, right? From 1 bar and 49.6 liters to 0.66 bar and 75 liters. Okay, so from this pressure and this volume, it goes to this pressure and this volume. Okay, undergoes a reversible isothermal reversible expansion at 298 Kelvin from 1 bar 49.6 and to what is that, 0.66 and 75 liters. Okay, so I want you to find all the 3 things, Q, W, and delta U or delta E. You're using delta E. Okay, delta E. I want you to find all these things.
Sir, can you repeat the question? Sir?
Yeah, sure. So the question is, what is it? Yeah, 2 moles of an ideal diatomic gas undergoes a reversible isothermal expansion at 298 Kelvin from 1 bar and 49.6 liters to 0.66 bar and 75 liters, right? They're asking you all the 3 things. Find Q, W, and delta E, right? So they've directly given you, no, you don't have to find what kind of process it is, just like previous problems. They have directly given you what kind of process the gas undergoes or the system undergoes, right? So they'll tell you that it's going to be a reversible isothermal expansion, right? Fine. Now, before even calculating, what? Okay, let me ask this. Okay, maybe Pranav. Are you there,
Yes,
Pranav?
sir. Yes, sir.
Pranav, can you tell me, without even going for the calculations, what is the value of delta E here?
Delta E.
Yeah.
Let me think and type it in. Ideal gas equation.
Okay. Ideal gas. Okay, fine. See, what is first? What is the formula for delta E?
So 1 second, sir. Q minus P delta V.
No. What I'm asking is, what is the formula for delta E? Last question, what we did for delta E?
So I have a doubt. Is temperature changing in this question? Have you mentioned change in temperature? Oh, no, sir.
Will this question have change in temperature?
It won't, no, sir. This
Exactly. Why? Why
It's
is it not having?
isothermal.
Correct. Right. Everything is on there in the question. It's an isothermal process. So obviously that means the temperature is constant. Right. So yeah, Venisha, the answer is correct, Venisha. So yeah, it is NCV delta T. Right. So now I can directly tell you delta E is 0. Is it not? Why
Yes,
delta
sir.
E is 0? Because I know delta E is equal to NCV del T, right? So NCV del T, that means change in temperature is what is required. But I know this is an isothermal process. That means constant temperature, delta T is 0. So definitely delta E is also 0. Right? Okay. Now rest two things. How will you go about it, people? Q1W. Okay, wait. Maybe Rahul, you can help me out with this.
Yes, sir.
Yeah, Kanna. So tell me how Q and W can be found out. Okay. Now I'll ask you maybe step by step. Now, what is the first law modification for an isothermal process? The first law mathematical form. How will it look for an isothermal process?
Q is equal to minus W.
Yeah, correct. Right. So Q is equal to minus W because I know delta E is equal to 0. Right. So obviously Q is equal to minus W. Right. So obviously, if I can find one of the things, either Q or W, I know the other stuff. That is the negative of that is what is going to be the answer. Okay, fine. Now, what can I find in this question, Rahul? I should find W or I should find Q, so that which we can find from this question.
Maybe W, sir.
Good.
W
Okay.
is equal to minus external pressure V2 del Q.
Okay, fine. So W is equal to minus P external del V is okay. But for this particular process which they have specified in the question, that is isothermal, reversible, expansion of an ideal gas, we especially did a derivation, if you can remember. There, work done was equal to what? You understood, right, what I'm saying? For this particular process, that whatever they have mentioned in the question, isothermal, reversible, expansion of an ideal gas, right? We did this obviously, right? And then we went on to derive a formula for W. Do you remember that?
I don't remember, sir.
Okay, cool, no issues. Maybe then I asked everybody, I guess. Okay, Rohan, what is the formula?
Use W equal to 2.303 into nRT into log V1 by V2.
Yeah, that is the formula. Guys, this is the formula which we have to use. Everybody remembers that we derived this, right? So we derived because since it's how to derive it, we said that dW is going to be equal to minus P external dV, right? So since it's an ideal gas, I put my P external as nRT by V. So dV by V will come. So dx by x. So if I integrate from this side and this side, V1 to V2, all that I did. So at the end, I was ending up with this equation, right? So for if they specifically ask you isothermal reversible expansion of an ideal gas, you should use this equation only, right? But if they didn't tell you anything about isothermal or nothing, then whatever the formula, W is equal to minus P external del V will work, right? Okay. So this is the formula which we have to use for an isothermal reversible expansion. Okay. So be very careful. Now that's it. I just have to substitute the values here. nothing else, right? So because initial volume was given, final volume is given. Now, if at all you don't want to use my V1 and volume, you can even go for pressures of the gas. Well, because we know P1 V1 equal to P2 V2, right? From Boyle's law, right? So I can, instead of V1 by V2, I can even write as P2 by P1. So either way, you can use your pressures. Pressure is given in the question, initial pressure, final pressure, as well as initial volume, final volume is given in the question, right? So yeah, and temperature is given. R value should be 8.314 again, because I want the answer in joules, right? Number of moles is also given, 2 moles. Log calculations, yeah, log calculation will be difficult. You can, if at all, now you are allowed to use your log books, right? But for certain calculations, I don't even need log books, people. Let me tell you how I'm going to do the problem. Okay. Okay, so 2.303, number of moles is 2, R is 8.314, temperature is 298 Kelvin, everything is given in the question, right? Log of, okay, let me write the log down, log of V1 by V2. Okay, what is the initial volume? Initial volume is 49.6 liters. Okay, people. See, 49.6 and 75 calculation is a little difficult, right? So what will I do is, instead of V1 by V2, I use P2 by P1. Why am I using this? Is because I'll get an easier calculation there. Okay, let me tell you how. Don't worry, right? Fine. So let me use P2 by P1 and hope everybody understood why am I using this just for the calculation purposes, right? But for your school, you can directly substitute the V1 and V2. Now I'm just making you say how to put it. Like if at all you're going to go for competitive exams, definitely you'll not be able to use log books. Like if at all some complex log values are there, they will give you in the question. They'll give you in the questions itself. But for normal, this calculations and all, they will not give you the log calculations. Okay. So anyways, so we'll try to do this. So yeah, so instead of V2 by V1, V1 by V2, I'm using P2 by V1 using my Boyle's law because it's an ideal gas. It follows Boyle's law, right? Fine. So P2 is what? P2 is 0.66, right? So P2 is 0.66. So let me write 0.66 as 2 by 3. I can write that, right? 0.66 is what? Is basically going to be 2 by 3. Again, if you divide 2 by 3, again you'll get 0.666666, right? So let me use that. This is my P2 value. Okay. What is my P1 value? P1 value is 1 bar. Yeah, it is 1 bar divided by 1. So anyways, I don't have to put it, or you can even put it by 1 bar. Okay. So basically what I have is basically going to be log of 2 by 3. If you want, you can remember, but it is actually very handy. Okay, it's actually very handy to remember the log values, people, right? Log to the base 10 values of 1 to 10, if you can remember. It's actually very, very, very useful. Okay, every time for small numbers, you don't have to go look at the log values. Okay, now let me tell you how do you remember. Okay, how do you remember the first 10 log values? More than that, definitely if you have, they will give it in the question. You don't have to worry. Okay, so let me start. What is log 1 value?
1, sir.
Log 10 value is 1. Log 1 value is 0. Okay, so log 1 value is 0. Please know this. Okay, fine. Next, log 2 is 0.3010. Okay, log 2 value is 0.3010. Log 3 value is 0.45, right? Okay, and log 4 is easy. Now, if you remember log 2, log 4 is easy. How? I told you that there can be certain operations that can be done in logs. How can I write log 4? Can I write 4 as 2 squared?
Yes, sir.
Right, now how can I write this? If you have powers, where it will go?
2 log.
2 log.
Ah, correct. Right, so this can be written as 2 into log 2. Right, so I know log 2 value. Log 2 value is 0.3010. So log 4 value is 0.6020. This is log 4. Okay, so again, log 5 you have to remember. There is no other go. Oops. Oh, fine. Anyways, I'll write it again. No issues. Okay, so log 5 is going to be around, say, I would say around 0.5. Okay. Oh, how will it be 0.5? It should be more than 0.6. It should be 0.7 approximately. Right? Fine. Log 6. Now log 6, how can I write it?
2 log 3.
Sorry?
2 into log 3.
Log of 2 into 3. Is that what you're saying?
Yes, sir.
Right. So this can be written as log of 2 into 3. Okay. Now again, this can be written as how? Log of A into B can be written as
Log A, log B, log A plus log B.
log A plus log B. Multiplication will become addition, division will become subtraction, right? So this can be written as log 2 plus log 3, right? So log 6 is log of 2 into 3. Log of AB can be written as log of A plus log of B, right? Again, I know this value, this value. So approximately it is going to be around 0.75. Okay. So that's my log 6. Okay. Log 7, again, you have to remember. So you don't have to remember the value. Log 8, how can I write?
4 into 2.
Correct. So this can be written as 4 into 2. But okay, that is one way. Or you can even write it as log 2 cube.
Yes.
Right. So this can be written as 3 into log 2. So 3 into log 2 will become what? 3 into 0.3 will become 0.9030. Right. So that's my log 8 value. And log 9, how can I write?
2 log 3.
Correct. So this is basically log 3 squared. I can write it as 2 log 3. Yeah. So 2 into log 3. Log 3 is basically going to be 0.45. So 2 into log 3 will become again 0.9. Say, you can ask me, sir, how log 8 and log 9 are same. There will be difference. You're doing it approximately. Okay. So you can keep it as 0.9. Again. Right. And log 10, lastly, log 10 value is 1. That's it. Okay. So if you can really remember this, see, you have to remember only log 2, log 3, log 5, and log 7. Right? If you can remember this, all the other things are going to be easy. At least log 2 and log 3, if you remember, most of the things you'll be able to have. You will be able to answer. Log 5, log 7 also you can leave it out. Okay. So log 2 value, log 3 value, if you can remember, all the other values can be found out. This is a very very useful trick, right? Whenever you wanna not waste time with your log calculations using log books, right? So yeah, so that's it. So we can now go for the problem. Isothermal
I have a
inverse.
doubt.
Yeah.
Can we take log 2 as approximately 0.3 or 0.30?
Sorry. Log 2 value as?
Approximately 0.30.
Yeah, you can use it. Log 3. Log 3 as log 2 as 0.3. Yeah, you can use it easily. Yes. Right.
Sir,
Okay. Yeah.
what is the log 7 value, sir?
That's a nice question. Log 7, where is it? Okay. Log 7, log 8 is, you can see that it is 0.9, and log 6 is going to be, where is it? 0.7. So this should be definitely around 0.8. Okay.
Okay, sir.
Right. Yeah. Cool. So we can actually go for the problem now. Right, so I had W is equal to 2.303 number of moles, R value, temperature value into log of 2 by 3 is what I had. How 2 by 3 came? I wrote 0.66 as 2 by 3, right? Okay, then that's it. Now you know log 2 value, you know log 3 value. You can go for this big calculation, and then whenever you find the answer, you can let me know, right? But anyway, eventually you have to do this calculations, and this kind of calculations you are expected to do for your school exams, right? So definitely you have to be a little fast in calculating. This is a very big number. You have to quickly calculate. But again, not in this class. Okay. So everybody understood how the problem goes. You have to use one formula. W is equal to 2.303 RT nRT log of V1 by V2 or P2 by P1, whatever it is, right? And then now if I find W, I obviously know what is the Q value. Q and W are equal and opposite, right? So whatever the W we found out, put a negative sign, that will be equal to my Q. And delta E we already found out to be 0 because it is going to be an isothermal process. Yes. Okay, cool. So I think that's enough number of problems we did. You want to do one more problem, maybe one last problem, because there is only 10 more minutes left. Maybe I can give you one more problem. Oh, second, people. Where is my marker? Yeah. Okay, fine. Now instead of doing a problem, we'll do an interesting thing. Okay, now what interesting thing we'll do is, see, we studied isothermal reversible expansion of ideal gas, and we have studied adiabatic reversible expansion of an ideal gas also, isn't it? Right. Now we are going to compare these two. Okay, so we are going to compare the expansions in isothermal, adiabatic, both reversible. We are going to compare. Okay, now we'll see where I'm going to get more work done, where I'm going to get less work done, and how to put it. Then you can understand that, I mean, obviously, the initial state and the final state should be same. That is P1, V1, P2, V2 in both the cases must be same. Only then I can compare. So if at all, so different states are there, different conditions are there, and you want to compare, it doesn't make any sense, right? So if at all I have same initial state, same final state, I'm going, right? So not necessarily. Okay, so if I do the form of a graph, people, right? Say I have a graph, P versus V graph. Okay, now both are expansion processes, right? So say one graph is like this, another graph is like this. Okay, now fine. If someone asks you which is for what, okay, what is that? And the first, say if I mark it as 1 and 2, okay. So if I ask you which is greater, okay, I mean which graph is for what? One is for isothermal or adiabatic, or say 2 is for what? Is it going to be isothermal or adiabatic? Is the question, right? Now how do you go about it, right? Fine. Now let me put it this way. Okay, so in an isothermal process, right? In an isothermal process, temperature change definitely will not be there. Okay, there will not be any temperature change, but heat change can be there. Q is not 0. Q you saw just equal to whatever the work done is there. That is my Q value minus of that, right? But in an adiabatic process, there is no Q at all, right? So that means there is no energy supplied, right? So what you have to understand is, people, now in both the cases it is expansion, right? So definitely the work is done by the gas. So obviously, right, whenever I tell you expansion, it is going to be work done by the gas, right? So for doing the work done, the gas has to get some energy, right? Okay. Now in your isothermal conditions, it's very straightforward. You can tell that, say I gave some 10 joules of heat to the system, and the system absorbed that, and the work was done by it. It's in isothermal, it is pretty straightforward, right? But in adiabatic, right, I am not able to supply any energy, but the gas still undergoes expansion, right? Now, can you tell me where is that energy coming from in an adiabatic expansion? In isothermal, we can supply heat, definitely, right? But in an adiabatic condition, when I'm not able to supply heat, right, where do you think the gas is getting the energy for the expansion or for the work done by the gas? Where is it getting the energy from?
Is it from the container it's kept in? Like its surrounding?
No. So if I don't supply heat, that doesn't that means that the gas will not have any energy. Think about it. So in a more specific way, right? Say in isothermal process, I can tell that the work is done at the expense of heat energy supplied, right? Okay, right. Now in an adiabatic process, work done is done at the expense of what? I gave you a clue also. If I don't supply any energy, that means that the gas doesn't have any energy.
It uses its own energy, sir, which it has.
Okay. What is the own energy called as?
Internal energy.
Exactly. Right. So in an adiabatic process, people, the work is done at the expense of internal energy. Right. So whenever a gas undergoes adiabatic expansion, the internal energy will always decrease. Why? Because some energy from the internal energy is taken, and that energy is only used for undergoing the expansion process. But in isothermal, it's not like that. Eventually, delta E is zero basically, because there's no temperature change, there is no internal energy change, but the work is done at the expense of the heat energy supply. You are supplying some heat energy, even though temperature is not changing, right? But in adiabatic process, the work is done at the expense of internal energy. Okay, internal energy will reduce, right? Now tell me, if the internal energy is reducing, right, what will happen to the temperature, final temperature? If I compare initial temperature and final temperature, how do you think the final temperature will be? Will it be lesser than the initial temperature or higher than the initial temperature?
In adiabatic, sir.
Yeah, so I'll repeat the question, right? So now we understood that in an adiabatic process, work is done at the expense of internal energy. That means before doing work, some energy is got from the internal energy and that is converted to work. The work is done, right? Now, definitely internal energy is reducing. That is understood, right? Now I'm asking, what about temperature? Say initially T1 and finally T2. Which is greater, which is lesser is what I'm asking.
T1, no?
Sorry?
Should be T1, no, sir?
T1 is what? Greater or lesser?
Greater.
Yeah, correct. Right? So T1 should definitely be greater. Now you can use your logic or you can use the formula. Right? What formula? Delta E is equal to NCV delta T. Right? Now that we are telling that the internal energy is decreasing, that definitely means delta E is negative. Is it not? That means final internal energy is lesser than the initial internal energy because some amount of energy is converted to work. right? So this is value is negative. N cannot be negative. The CV cannot be negative. So the only way it can be negative is this being negative. So this is basically going to be T2 minus T1, and this can be negative if T1 is greater. That is, the initial temperature is greater and the final temperature is lesser. Okay, now please keep this in mind. Whenever a gas undergoes adiabatic expansion, it always causes cooling effect. Okay, whenever a gas undergoes adiabatic expansion, it's reversible or irreversible, doesn't matter. But whenever a gas undergoes adiabatic expansion, right, you will always see that there's a cooling effect, because some amount of internal energy is lost by doing work, and obviously temperature will also reduce, right? So the final temperature will fall. This causes a cooling effect. Okay, fine. Let you take this as a homework, right, and come up with an explanation for which is adiabatic and which is isothermal. Okay, so go for it, right? And next class maybe we'll discuss, right? Fine. I hope this understood. Whenever adiabatic expansion happens, it always causes a cooling effect, because again, for whatever reasons I told you, right? Okay, people. Any other questions? Wait. Instead of okay, you do this as a homework, but you can answer this question now. I have a chamber. Here I have vacuum. Okay, and say, right, there's a piston, there's a gas, right? Now say I had a 1 kg mass, it was in equilibrium. Okay, now I removed the 1 kg mass. Obviously the piston will move up, right? What is the work done here? Hope you understood my question, right? I have a chamber in which there is vacuum, right? Okay, and I have a piston placed. I had a 1 kg mass, it was in equilibrium. Now I removed the 1 kg mass, so obviously the piston moves up, right? Now I'm asking you, what is the work done? Yes.
Sir, is it 0, sir?
Very good. How?
Vacuum, so no external pressure is there.
Exactly, right? So whenever you have vacuum, people, that means there are no gases, no atmosphere, nothing is there. So there is external pressure to be equal to 0. Okay, so whenever you see that the gas is expanding against vacuum, or against, we cannot say, expanding in vacuum, right? So definitely at that time W is 0, because P external del V, P external is 0. There is no external pressure, right? And this particular condition is what is called as your free expansion of a gas. Right? So this particular phenomena, the expansion of a gas under vacuum, right, is what is called as free expansion of the gas. And there can be question, 1 mark they can ask you, what is the work done in free expansion of a gas? You should tell that the work done is 0, because under vacuum the external pressure is 0. Okay, this term is very, very important. I have seen a lot of times questions coming from this free expansion of a gas, expansion of a gas under vacuum. Okay, fine, people, we'll stop with this. Okay, so next class you bring the answer to this question for me. Okay, which will be adiabatic, which will be isothermal, right? And we'll discuss, right? So if you don't have any questions, we can wind up. Is there any questions, any doubts? Okay, so I assume that there are no questions. Thank you, people. Bye bye. We'll see you again.
Thank you, sir.
Thank you, sir.